Welcome to our presentation for Qiskit Hackathon Europe 2021. Our project title is QSVM for Big Data Classification on Astronomical Events. Machine learning algorithms require a lot of data to train on. On the other hand, our space programs provide abundance of data. However, the biggest challenge with astronomical data is that it's extremely costly to label the data. As a result, the field of astronomy struggles to leverage the power of machine learning algorithms due to lack of adequate amount of data. Classical machine learning algorithms usually fall short in classification tasks where training samples are limited. However, many literatures have showed that quantum machine learning algorithms can tackle the challenge of limited training samples by outperforming classical machine learning algorithms, even with a limited number of qubits available in the current hardware. Therefore, in this project, we aim to explore the feasibility of implementing QSVM for the classification of astronomical data with a minimum amount of training samples. Our work is going to open the door for highly significant astronomical projects like FINC and LSST, where they can leverage the quantum-enhanced machine learning algorithms in order to study the universe on a broader and deeper scale and know the unknown. We are trying to answer two different research questions. Our first question is, can a hybrid approach of classical and quantum machine learning algorithms outperform conventional machine learning algorithms? Our second question is, can we achieve quantum speedup with this hybrid approach of implementing quantum machine learning using a classical training dataset? Let's see.
So in order to answer this question, we work with data release 16 from Sloan Digital Sky Survey. This data set contains 100,000 observations with 16 variables and one multi-class target. We use this data set also as a proof of concept for the future plastic data set mentioned in our report from FINC projects. So as you can see, on the right-hand side is our modeling structure, and on the left-hand side is our benchmarking structure. We start our modeling structure with loading and understanding the data set. In this step, we're trying to find which features are most important and contribute the most to the targeted variables, and that included in feature engineering. Second step is the step that we train and test our model. We test and train our model in two phases, in classical SVM with kernel method and quantum SVM with the feature mapping. And then finally, we compare our result in model performance and runtime test. We run our trained model in different platforms, local QASM simulator, IBM online QASM simulator, and real quantum device. And as you can see here, these are our findings that summarized in table 2. So after hypertuning different methods in dimensionality reductions together with feature mapping, we arrive at the conclusion is that when at 100 training sample, SVM and QSVM perform very similarly. But when we increased our sample size to 200 sample size, QSVM outperformed SVM. However, and you can also see at the runtime test, classical SVM took much shorter time to train and test compared to our QSVM. So what does that mean for us, our findings? Our findings open a new door for us to apply our work on the FINC projects, that if we can apply QSVM in FINC project, we're able to contribute to their work in the preparation for this biggest astronomical run in 2023 called LSST. To conclude our presentations, we would like to sum up our experience, amazing, incredible experience in our research project by a poem created by our team member, Rita. Rita, please.
How colorful and capricious the journey was with Discord, Slack, Medium, integral parts of the Constellar bus. Eureka moments, albeit errors in syntax and semantics, it felt like a cruise vacation in the Atlantic. Grateful we are to our friends, IBM and mentors. Because of them, this hackathon we adore. Excited we are to see Qiskit dominate the world. Very soon, its beauty, potential will be embellished and pearled. Thank you very much.
Thank you very much.